Problem 8 deals with deletion mapping. In this case, we're using phage again, but this need not be phage. This is something that we can do with any diploid organism. So in this case, we have a series of known mutations. So lines 1, 2, 3, 4, and 5 have deletions which we know where those are, and they're in different places along the chromosome. In this case, number 5 actually has 2 different mutated regions. And in this experiment, we're going to take 5 new mutations, series of point mutations, A through E, and we're going to do these co-infection experiments and look for the ability to generate wild-type progeny. So we're going to look for the ability of these things to recombine and generate wild-type sequences. So remember then that the idea is that if these 2 different phage have mutations in 2 different locations, they'll be able to recombine to give you a chromosome that has the 2 mutations, but also a wild-type sequence. And this wild-type sequence will be able to make plaques. However, if you have a situation where there's a mutation on one strain, say one of these point mutations, and you cross that to one of these lines that has a deletion, then if this section of the chromosome is missing over here and is mutated over here, then there's no way that these things can recombine to give you the wild-type phenotype. So you'll never get that wild-type plaque-causing phenotype back out of this. So this is the general idea. There's places where we see that when we do these crosses between these known deletions and these new point mutations, if we see situations where we can't get any wild types back out, that everything is minus, then we know that these point mutation must be in the same place where this deletion is. So these sorts of problems are pretty easy to do. So if we look at what happens with strain A, so when we cross it to these lines, these are what we get. So where we get pluses means that when we cross to deletion 1, deletion 2, or deletion 4, we're able to recombine and get wild-type phage back out, meaning that the mutations are not in the same place as those deletions. The more informative things are the places where we do not get a recombination to get wild-type phage back out, where we don't see rescue or complementation. So in this case, for mutation A, we don't see rescue with A, we don't see rescue with 3 or 5, deletion 3 or deletion 5. So basically what we want to do then is find a place where 3 and 5 both have the same region deleted, which in this case would be about here. And this makes sense with the idea that 1 rescues, 2 rescues, and 4 rescues, because those sequences are all intact in those lines, but this region is deleted in 3 and in 5. So the position then of point mutation A should be someplace about here. So if we move on then to B, we see that it does not rescue with 2, this particular mutation, but does rescue with everything else. And that would make sense with the mutation that's about in this region, a region where 2 is deleted, but all the other strains are wild type. So B, I'd put about here. C does not rescue with 3, but does with the other ones. So it'd be a region where 3 is deleted, but none of the other ones are, which would be up here. So we know that it's not in this part of the deletion with 3, because then 5 should not rescue either. But 5 does, so we can kind of assume that it's someplace a little bit over this way. So we put C over here. D then does not show rescue with 1, but rescues with everything else. So we want a region where 1 is deleted and everything else is wild type, which would put it about here. And then finally with E, we see it rescues with everything except 4 and 5. So 5 has deletion in 2 places, one here and one here. But we know that 4 and 5 both fail to rescue, so it must be a place where both of these are deleted, which would put it over here. So then the order is what they're actually asking for. What's the order that's most consistent with these data? and it would be what's shown up here. So C, A, D, B, E would be the order of these mutations along the chromosome.